Okay, hello everyone. Welcome to Module 10, which is all about changing electric fields. So last week we focused on Faraday's law and Lenz's law, which emerged from changing magnetic fields. This week is changing electric fields. And the topics are divided into sort of three sections, or how I organize them on collages into like three main concepts. The first concept is something called displacement current. And then the second concept is emerges actually from displacement current. And it's basically like, how do electromagnetic waves propagate through space? So we'll take a look at that. The collage is organized into different like videos that show some examples of like how do like antennas transmit information through like radiative waves. So take a look at that. And then the third section is like, how do those waves carry energy? And so basically, I'm going to organize this into two different videos. I'll make a video, this one, on displacement current, and then I'll make another video that just encompasses like propagation and energy. So the topics are relatively light this week compared to last week. Okay, so let's start out by talking about displacement current. So displacement current is a weird concept. It's actually a theoretical concept that emerges from a breakdown in Ampere's law. And it comes specifically from like a discontinuity that emerges when you consider a charging capacitor. Okay, so let's imagine that we've got a capacitor that we're charging up. Okay, and so we've got like a plate here and here. And let's say that we've got like some current going to this plate, and we've got a buildup of positive charge here. And then we've got that same current leaving this plate. And we've got a deficit of positive charges. And so we'll denote that with just negative charges being left behind on the plate. So remember when we talked about capacitors, we said like the way to think about like the charge flow is like imagine that this is connected to like a battery. This is just a review of capacitors. So this is the positive terminal of the battery, and that's the negative terminal of the battery. So like it's like we define current as the flow of positive charge. So positive charges are physically like flowing to this plate here and building up. Okay, and then positive charges are like flowing from this plate here, leaving behind a deficit of positive charges, like i.e. negative charges, and they're flowing back to this negative terminal of the battery. Okay, so let me erase this. Let me erase this part because that's not necessary for displacement current. Okay, so that's the situation. I'm gonna denote these currents here as IC for reasons that you'll see in a second. So I'm gonna say that IC is like conduction current. Okay, so that's like real current that's actually going to those plates. Okay. Um, and you know, like they're the same, right? Like IC on the left is equal to IC on the right. So the question is what happens? And we kind of glossed over this when we initially talked about capacitors, but what happens to the current in between the plates? Okay, and a secondary question is there an electric field between the plates? And the answer to that is, of course, yes, right? We know that there's an electric field. We know that there's a field going from the positive charges to the negative charges. Okay. And if we were to draw, remember like a Gaussian surface like on this plate that encompassed all of those charges, like a Gaussian surface. And we were to calculate the electric flux, that would be equal to the Q enclosed divided by epsilon naught. Okay, but remember that as a capacitor is charging up, the Q enclosed is increasing. Okay, like as more and more charges accumulate on that plate. So therefore, like the change in current or the change in charge as a function of time is not equal to zero. It's equal to some like value that's time dependent, right? So it's like the change of it's epsilon naught times dt as a function of the flux. Okay, so like as more and more charge builds up on the plate, the electric field gets stronger and stronger, and the flux, like through some Gaussian surface, gets larger and larger. Okay, so we could say that like the current, like for lack of a better word, between the plates, which is like a theoretical construct, is not the same as the current going through the wire, right? Like so we would say like that like the conduction current is just like dq dt, and this is the current in the wire. Okay, but in between the plates there's this other kind of like for lack of like it's a theoretical current. And the way I think of it is it needs to exist to make the math work. And I'll show you that in a second. But it's also more than that. Like it needs to be there in order for the continuity of electromagnetic waves to exist. Like electromagnetic wave propagation, electric fields and magnetic fields are coupled together. You can't break them apart. If you have a changing electric field, which you do because you have a buildup of charge on the capacitor plates, that has to produce a changing magnetic field. And then that produces a changing electric field, changing magnetic field, and that's how electromagnetic waves propagate through space. So you can't have a changing electric field like you do when you have charges building up on a capacitor plate without it leading to a changing magnetic field. Okay, and if there is not this theoretical displacement current in between the plates, then Ampere's law breaks down. Okay, so like the displacement current is a theoretical current that must exist for Ampere's law not to break. Okay, like if that theoretical current isn't there, then Ampere's law breaks, like it breaks down. It doesn't make sense. Okay, and I'll show you that in a second. But just understand that it's like it's basically something that exists. Displacement current is something that exists, A, to make the math work out for Ampere's law, and B, because it has to be there in order for like electromagnetic waves to propagate through space. Like if like you can't have a changing E field must lead to a changing B field. Okay, that is literally how EM waves propagate. Okay, so you can't have here in between here, you have a changing E field as the charges build up on the plates. So that must lead to a changing B field. Okay. And the displacement current is the sort of added term that that makes Ampere's law not like break down. Okay. So like how we define the displacement current is really just here. Like this is the displacement current. Okay, it's just the it's just epsilon naught times the change in electric flux. Sorry. As a function of time. Okay. And so this is the current between the plates. Okay. Another way to write it is so like ID, displacement current, is so it's epsilon naught. Remember what electric flux is. Electric flux is just the dot product between the electric field and the area vector. So assuming those two things are pointing in the same direction, we can just rewrite it as like dIE over dt is just A, because that's a constant, times the change in electric field as a function of time. Okay, so that's the displacement current. Okay, now let's look at it from like since our whole premise is that it exists so that Ampere's law doesn't break down. Let's look at Ampere's law, and I'm gonna have to like insert another page here. Okay. Okay, so Ampere's law, oops. Remember what Ampere's law says. Ampere's law is just that if you pick some path like B dot dl, if you draw a line around a magnetic field, right, a path like a path integral, that path is going to be equal to mu naught times the enclosed current. Okay, so if you draw a line around, if you draw like an Amperian loop around like this part of the wire, right, out here, like the Q enclosed is the conduction current, right? However, if you draw a loop around this part, then the I enclosed is the displacement current. So to extend Ampere's law, to encompass the displacement current, Ampere's law turns into something called Ampere Maxwell, because it was Maxwell who discovered this displacement current. So it gets there's kind of a correction factor in the Ampere Maxwell law, which adds in the displacement current term. Okay. So now Ampere Maxwell's law, which is a mouthful, Ampere Maxwell law says that if you integrate around a path of a magnetic field, that is going to equal basically the conduction current plus the displacement current. Okay. And we'll do an example in a second so you can see exactly what that looks like. So the question, so another like question is like so we set up here that there's a changing electric field in between the plates, right? The question now is, should we expect a B field between the plates? And the answer to that is yes, right? And for the reasons that I just said, like a changing E field has to lead to a changing B field. Okay, otherwise, like electricity and magnetism breaks down. Like this is a fundamental fact of electricity and magnetism, is that if you have a changing E field, you must have coupled with that a changing B field. So there's both of these between the plates. Okay. And like, I just want to just make sure that it's really clear that this is essential for how E&M waves propagate through space. Okay. And when I say space, I mean empty space. Like one of the most amazing things about electricity and magnetism is that E&M waves can propagate through a vacuum. Right. And in fact, like, I mean, that is like behind most of the world's like telecommunications, right? Is the fact that you can propagate E&M waves like through space, through empty space. Okay, it's like basically how like the entire like world of telecommunications works. Okay. So I want to make sure it's clear that without this idea of a displacement current, which again is like a theoretical construct to make Ampere's law not break down. Um, like without this, you would have an E field that is generated from the capacitor plates charging up. You'd have like a changing E field that would like not lead to a changing B field. Right? And then this would cause like this would break the chain of EM wave propagation. So displacement current, it seems like a weird construct, but its existence allows like electricity and magnetism, the connection between the two things not to break down. Okay. Um yeah, so that's most of what I wanted to say. So why is displacement current important for electromagnetic wave propagation? It shows its existence is essential for showing that a changing E field leads to a changing B field. Okay. Um, Even in empty space, like in between the capacitor plates. Okay. Without any moving charges. Okay. And that's the sort of key point. Right? Like the charges are just building up on the plate. That's generating an E field, and then that changing E field it like gives rise to the changing B field. So if you didn't have displacement current, then that connection would break down. Okay, let's do this example problem. And I think this, yeah, I constructed this example problem to help you with one of the problems on the challenge for this week. So here we've got a parallel plate capacitor. It has a plate area of 0.02 meters squared, and the electric field between the plates is increasing at a rate of 3 times 10 to the power of 6 volt meter per second. And what we want to know is what is the displacement current between the plates? Okay, so let's use this as an opportunity to talk about something else. Okay, let's draw it. Okay, so I've got the conduction current here and here. This plate's charging up positive. Okay, this plate's charging up negative. Okay, let me draw like a surface with two different sort of parts to it. Okay, so let me draw like a surface, and it's a continuous surface. Okay, so I can use it in Ampere's law. So like here's let's say it's kind of like that on one side. So let me call that like surface one. And then let's say it kind of bulges out here and like encompasses the positive plate there. So let me call that part surface two. Okay. So let's consider Ampere's law through both surfaces. Again, like I want to show you the purpose of this is to show you kind of like how it breaks down if we don't take into account the displacement current. Okay, so like Ampere's law basically says that like this should be true. This or like a path integral around any path like of B dot DL should equal um this no matter what the surface looks like. Okay, that's what Ampere's law says. Remember, like when we did it, we made like a big deal about the fact that we could draw like literally any surface. It didn't matter the shape of it, and that this relationship should hold true. Okay, let's look at the two surfaces. Just with like and this is just the regular Ampere's law, not the enhanced version. Okay, so for surface one, which is just the simple one, the simple one on the left. I enclosed just equals I. Okay, and therefore B, if I integrate around that path, right, like it would just be a perimeter 2 pi r. So B dot dl would equal mu naught just times I enclosed. Okay, so just the regular like Ampere's law that we did a few weeks ago. Okay, surface two, um, like using again the regular Ampere's law would say that I enclosed is actually zero, right? Because there's no like forget about displacement current for a second. There's no current enclosed in this surface. Okay, there's no current going through here. Okay, there's no because remember there's no like real current between the plates. Okay, so that would say therefore that like this B dot DL would equal zero. Okay, and this creates a problem. The fact that these two results don't equal the same thing um is like it creates like a discontinuity, like to use a term from math. Okay. So and we know that between the plates, there's charge building up, and that is creating a changing electric field, which must lead to a changing magnetic field. And therefore, according to Ampere's law, there has to be a current, right? Because like a B field has to have a current. Right? So in that way, Ampere's law breaks down because like these two things do not equal, these two surfaces yield different results. Okay. So therefore we must expand Ampere's law to the Ampere-Maxwell law. Okay, so there's a breakdown in Ampere's law. Because the two surfaces yield different answers. Okay, and so therefore we must expand. And this is what Maxwell did. Ampere's law. So the Ampere-Maxwell law. Maxwell law. Okay, and the Ampere-Maxwell law is just B dot dl, same left-hand side, equals mu naught times the regular conduction current plus E naught times the change in electric flux as a function of time. Okay, so this, remember, is the regular conduction current going through the wires. Current in wire. And then this is the displacement current. Okay. So that's sort of like just I mean, it's just kind of showing you like why the Ampere-Maxwell law emerged is like this breakdown in the regular Ampere's law. But now we need to actually calculate answer the question, what is the displacement current between the plates? Oh, actually, before we do that though, hold on. Let me insert another page. Okay, let's use let's now use the Ampere-Maxwell law to look at the two surfaces. Okay, so now we can say that surface 1 has just the regular like conduction current, and surface 2 has the displacement current. So that's going to be mu naught times epsilon naught times the change in electric flux as a function of time. Okay, and I can use that fact. So like the point is that like together they like so together we can say that like there's not an inconsistency, like one thing is no longer yielding a zero value as it was before, right? So we can say that together they're giving you this d the change in flux over the change in time. Okay, so there's now like no longer a discontinuity, a discontinuity as there was when this one was giving you like a zero current. Okay. So now let's calculate it. Okay, so the question is, what is the displacement current? Okay, so displacement current can be calculated just by multiplying. So you've got epsilon naught times the change in electric flux as a function of time. So remember what electric flux is. It's just E dot A. Okay, so I can rewrite this as epsilon naught times A, which is not changing, times the change in electric field as a function of time, which I'm given in the problem. Okay, so epsilon naught is just a constant. It's 8.85 times 10 to the negative 12 farads per meter. The area I'm given, let's see what the area is way back here, 0.02 meters squared. 0.02 meters squared. And this is given also by the problem. This is just 3, I think, isn't it? 3 times 10 to the 6. So this is 3 times 10 to the 6 volts per meter second. So 3 times 10 to the 6 volts meter second. I multiply that out and I get amps. So the displacement current is 5.3 times 10 to the negative 7 amps. Okay, and that's the answer. So just to review, So like the the fact that so Ampere's law breaks down because through one surface we get a current, like through surface one we get a current, and through surface two we get zero, right? Because there's like no current going through surface two. So that basically indicated that like Ampere's law, as it was written, doesn't work for this one sort of weird situation where you have electric charge building up on a plate, and it's clearly like, it's clearly leading to an electric field between the plates. And we know that while that plate is charging up, that electric field is changing, and a changing electric field always leads to a changing magnetic field. And Ampere's law says that if you draw a path around a magnetic field, that path should include some current. And if it doesn't, then that's a problem, right? So that's the reason Ampere's law breaks down. Maxwell, who, by the way, all of the equations that we've been talking about this semester, with the exception of Coulomb's law, all of those equations, like Gauss's law, Ampere's law, Faraday's law, they are collectively referred to as Maxwell's equations. And I put a little section on collage, basically like giving the like an overview of what those equations. We've now covered all of them. And so you can take a look at that. I made a summary on collage of like what Maxwell's equations are. So take a look at that. But this is like the last one, basically. Is this amendment to Ampere's law that allows us to correct for displacement current. Okay, so that's all I wanted to say about displacement current. In the next video, I'll talk a little bit more about E and M, wave propagation and energy.